13.2 Free fall acceleration and the gravitational force. The outline of this video is as follows. We will begin by connecting the familiar concept of weight, which is mass times g, to Newton's universal law of gravitation. This will bridge our everyday experience with a more fundamental description of gravity. Next, using this connection, we will derive an expression for the free fall acceleration, g, right at the surface of the Earth. This will show us how g arises from the Earth's own physical properties, like its mass and radius. We will then explore how the value of g is not constant, but actually decreases as we move to higher altitudes. We will look at a table of data that clearly illustrates this variation with distance. Finally, we will apply these concepts in a practical example to calculate the average density of the Earth. This calculation will demonstrate the predictive power of the gravitational principles we have discussed. This slide shows how we can connect our everyday concept of weight with Newton's universal law of gravitation. This is an important step because it will allow us to understand the origin of the free fall acceleration, g. First, let us recall from our study of forces that an object's weight is the gravitational force the Earth exerts on it. We calculate this using the familiar formula. F equals m times g, where m is the mass of the object. Second, we now have a more general expression for this same force from the law of universal gravitation. For an object at the Earth's surface, this force is given by F sub g equals the universal constant g times the mass of the Earth, m sub e, times the object's mass, m, all divided by the square of the Earth's radius, r sub e. Since both equations describe the exact same force, we can set them equal to each other. This gives us the key relationship shown at the bottom. M times g equals the quantity g, m sub e, m, all over r sub e squared. This equation links the local freefall acceleration to the fundamental properties of the Earth. We can now derive an expression for the freefall acceleration, g. This is significant because it reveals that g is not just an arbitrary constant, but is instead a direct result of the Earth's fundamental properties. On the previous slide, we equated an object's weight, m times g, with the universal gravitational force it experiences. The key insight here is that the mass of the object, little m, appears on both sides of that equation and can therefore be cancelled out. This simplification leaves us with the equation shown, g equals the universal gravitational constant g times the mass of the Earth, m sub e, all divided by the square of the Earth's radius, r sub e. When we substitute the known values for g, the Earth's mass, and the Earth's radius, this formula calculates to approximately 9.80 meters per second squared. This is the origin of that familiar value. The essential result is that the acceleration of a freely falling object near a planet's surface depends only on the planet's mass and radius, not on the object's own mass. Let us now see how the gravitational force changes when an object is at some altitude above the Earth's surface. This is important because it shows that the acceleration due to gravity, g, is not a universal constant, but depends on your locations. Imagine an object, like a satellite, at a height above the ground. The law of universal gravitation depends on the distance between the centers of the two masses. So the distance r we must use in the formula is the Earth's radius, r sub e, plus the altitude h. This means the magnitude of the gravitational force, F sub g, is given by g times the mass of the Earth, m sub e, times the object's mass, m, all divided by the quantity r sub e plus h squared. We can also express this force as the object's weight at that specific altitude, which is F sub g equals m times g. Here, g represents the value of freefall acceleration at that height h, which will be less than the value at the surface. The key takeaway is that gravitational force weakens as an object's altitude increases, because the distance from the center of the Earth becomes larger. Now we will see how the free-fall acceleration, g, changes as we move away from the Earth's surface. This is important for everything from satellite orbits to understanding the extent of Earth's gravitational influence. We can find the value of g at any altitude by using the two expressions we have for gravitational force. The first is an object's weight, which is its mass, m times g. The second is Newton's universal law of gravitation. At an altitude h above the surface, the total distance from the Earth's center is the Earth's radius, re, plus the altitude h. When we set these two force equations equal to each other, the mass, m, of the object cancels out. This leaves us with the expression shown here, g equals g times the mass of the Earth, all divided by the quantity re plus h squared. This result tells us that as the altitude h increases, the value of g decreases because h is in the denominator. As an object gets infinitely far away from the Earth, its weight approaches zero. Therefore, the acceleration due to gravity is not a constant, but instead weakens as altitude increases. This slide presents Table 13.1, which shows us exactly how the free-fall acceleration, g, changes with altitude. This table puts concrete numbers to the equation we just discussed. The left column lists the altitude, h, in kilometers above the Earth's surface. The right column shows the corresponding value of g in meters per second squared. At an altitude of 0, we see the familiar value of 9.80. As the altitude increases, the value of g gets smaller. For example, at 4,000 kilometers up, g is only 3.70 meters per second squared. This directly addresses a common misconception about astronauts in orbit. The International Space Station orbits at about 400 kilometers. According to this data, the gravitational acceleration there is still quite strong, about 90% of what we feel on the surface. Astronauts feel weightless because they are in a constant state of freefall, not because gravity has vanished. As the table shows, you have to go very far away for the acceleration to approach zero. The key takeaway is that gravitational acceleration is not a constant, but decreases as your distance from the Earth's center increases. Let us pause for a moment to check our understanding with a quick quiz. The question asks for the magnitude of acceleration for a baseball in a circular orbit, launched from a very tall mountain. This problem connects the idea of orbital motion with our new formula for gravitational acceleration. First, remember that an object in orbit is constantly accelerating toward the center of the Earth. It is in a state of continuous freefall. The force causing this acceleration is the Earth's gravitational pull. From Newton's second law, this means the ball's acceleration is simply the local value of the freefall acceleration, g. We just learned that the value of g decreases as your distance from the center of the Earth increases. The problem states the baseball is on a very tall mountain, meaning its altitude is significantly above sea level. Because the baseball is orbiting at an altitude above the surface, its acceleration must be slightly less than the 9.80 meters per second squared we experience at the surface. Therefore, the correct answer is. It is a common mistake to think there is no acceleration in orbit, but without it, the baseball would fly off in a straight line. We can now apply our understanding of gravity to calculate a fundamental property of our planet, its average density. This example is a great illustration of how gravitational measurements made at the surface can reveal information about the Earth's internal composition. The problem asks us to find the Earth's average density, given only the value of g at the surface and the Earth's radius. To solve this, we will begin by creating a simplified conceptual model. We will assume that the Earth is a perfect sphere and that its density is uniform or constant throughout its entire volume. This assumption is a key simplification. We know the Earth's core is much denser than its crust, so the density is not actually uniform. Because of this, our calculation will yield the average density for the planet as a whole, not the density at any one specific location. This model provides the necessary starting point to connect the surface value of g to the overall mass and volume of the Earth. Now that we have an expression for the mass of the Earth, we can use it to find the Earth's average density. We will do this in two main steps. First, we will combine our equations, and second, we will simplify the result algebraically. We start with the basic definition of density, which is mass divided by volume. We substitute our expression for the mass of the Earth, m sub e, into the numerator. For the volume, we use the standard formula for the volume of a sphere, which is 4/3 times pi times the radius cubed. This gives us a large, complex fraction for the density, rho sub e. Finally, we simplify this expression. Notice that the term for the Earth's radius squared in the numerator cancels with 2 of the 3 factors of the radius in the denominator. After rearranging the terms, we arrive at our final, simplified equation. The average density of the Earth is equal to 3 times g, all divided by the quantity 4 times pi times g times the Earth's radius. Plugging our known values into the equation for the Earth's average density gives us a fascinating result. When we substitute 9.80 meters per second squared for g, the value for the gravitational constant g, and the Earth's radius, the calculation yields an average density of 5.50 times 10 to the power of 3 kilograms per cubic meter. Now, what does this number actually mean? To find out, let us compare it to something familiar. The density of a common surface rock, like granite, is only about 2.75 times 10 to the power of 3 kilograms per cubic meter. This value for granite is roughly half of the average density we just calculated for the entire planet. This difference leads to a powerful conclusion. The material in the Earth's interior, particularly its core, must be significantly denser than the rock we see at the surface. This example shows how measuring g and g allows us to infer key properties about the deep, unseen structure of our own planet. Let us summarize the connection between an object's weight and universal gravitation. An object's weight, which we calculate as m times g, is simply the local gravitational force acting on it. Equating this with Newton's law of universal gravitation allows us to derive a formula for the freefall acceleration, g. At the Earth's surface, the value of g depends directly on the Earth's mass and radius. Crucially, this means g is not a fixed constant. It decreases as your altitude above the surface increases. These gravitational principles are powerful tools. For example, they allow us to use the measured value of g to deduce large-scale properties of a planet, like the average density of the Earth. In short, the familiar freefall acceleration, g, is a direct consequence of universal gravitation, and its value is determined by the mass and size of the planet. Let us work through these review questions to solidify our understanding. For the first question, we can find the surface gravity on a new planet by looking at our equation for g, which is the universal gravitational constant g, times the planet's mass, m, divided by its radius r squared. The question states, the new planet has twice the mass of Earth, but the same radius. If we substitute 2 times m into the equation, the resulting value for g will be twice that of Earth's. Now for the second question. Is the gravitational force on an astronaut in orbit zero? The answer is a definite no. The force of gravity is what keeps the astronaut in orbit around the Earth. Remember that the gravitational force depends on the inverse square of the distance between the objects. The astronaut is 400 kilometers above the surface, which is a finite distance. Therefore, the gravitational force is not zero. it is simply a bit weaker than it is on the surface. This gravitational pull provides the centripetal force necessary to keep the astronaut moving in a stable circular path.